Have you ever really, truly stopped to think about the screen you're looking at right now? Not what's on it, but what it actually is. It feels like this simple, solid piece of glass. But what you're holding is easily one of the most complex and precisely manufactured objects humanity has ever created. Let's pull back the curtain on this little engineering miracle. So yeah, how do you actually build a window into the digital world? It's a journey that goes from absolutely massive to unimaginably small, from basically molten sand to billions and billions of perfect microscopic switches. So let's follow that journey, step by incredible step. Everything, and I really do mean everything, starts with the canvas. But this isn't just any old piece of glass. Oh no, this is a piece of material science so advanced, it's pretty much what makes our entire digital life possible. It all starts here, with what they call mother glass. And you've got to understand, this stuff has to be perfect. We're talking atomically smooth, chemically pure, just flawless. Any tiny imperfection here, even one you could never see with your own eyes, would cause a ripple effect and just ruin millions of dollars worth of displays down the line. It has to be perfect from the get-go. Now, what's really fascinating here is that the story of how we got bigger, better, and cheaper screens is really just the story of bigger mother glass. The huge leap forward wasn't just about making better pixels, it was about scaling up this first sheet of glass. Every time they jumped up a generation, it meant they could cut way more screens from a single sheet. The efficiency went through the roof, costs plummeted, and that right there is the biggest reason you can go buy a huge, beautiful TV today without taking out a second mortgage. And to put today's Gen 10 mother glass into perspective, it's over 3 meters on its longest side. That's 10 feet. It's wider than a standard basketball hoop is tall. And on this absolutely colossal, perfectly flat, perfectly clean sheet of glass, we're about to build billions of microscopic electronic components. It's wild. All right, so we've got our glass canvas. What's next? Well, now we have to give it a nervous system, a super complex electronic grid that's going to control every single point of light with unbelievable speed and precision. And the hero of this part of the story is the thin film transistor, or TFT for short. The best way to think of it is as a microscopic light switch. Every single tiny dot of red, green, or blue light that makes up the picture on your screen, each subpixel, is controlled by at least one of these little guys. A 4K TV has something like 24 million of them. Your phone has millions. It's a whole invisible city of switches built right on top of that glass. So how in the world do you build billions of transistors? You basically print them, one atomic layer at a time. This 3-step cycle is the heart of the whole process. First, you deposit a perfectly even, super thin film of a material, say silicon for the transistor itself, or a metal for the wiring. Then, in a process called photolithography, you use UV light and what's basically a stencil to draw the circuit pattern you want. And finally, you etch away all the material you don't need, leaving just the pattern behind. And get this whole cycle of deposit, pattern, etch, it's repeated more than a dozen times to build up all the complex layers of the final circuit. Okay, deep breath. We've built the electronic brain. The switches are all there, ready to go. Now we have to add the parts that are actually going to make the light and the color that you see. And this is where we get to the 2 main technologies you see today, LCD and OLED. Think of it like this. An LCD is all about blocking light. There's a big, powerful backlight that's always on, and the transistors control tiny liquid crystals that twist to either block that light or let it pass through a red, green, or blue filter. But OLED is totally different. It creates light. Each and every subpixel is its own microscopic light bulb. It lights up on its own. And that, by the way, is why OLED screens can have those perfect, inky blacks. When a pixel is supposed to be black, it's literally just turned off. No light, no glow, nothing. So for an LCD, you're essentially making a high-tech glass sandwich. You have another sheet of glass with a microscopic grid of red, green, and blue color filters on it. Then, using this really cool technique called one-drop filling, a machine puts one perfect, tiny droplet of liquid crystal into each pixel zone. Finally, the 2 sheets of glass, the one with the transistors and the one with the color filters, are sealed together in a vacuum, trapping that liquid crystal perfectly in between. Now, OLEDs have a totally different challenge. You're not filtering light, you're creating it. So you have to deposit the actual light-emitting organic materials for red, green, and blue into exactly the right spots. This is usually done with an incredibly fine metal stencil called a shadow mask, making sure the right color material lands only on the right subpixel. It's an insanely delicate process. But here's the huge catch with OLEDs. Those organic light-emitting materials, they are ridiculously fragile. They are so sensitive that if even one single molecule of water or oxygen touches them, it can permanently damage them and kill the pixel. Dead. For good. So this was a massive problem for engineers. How do you perfectly seal billions of these fragile little things from the outside world for years and years? The answer is a brilliant technology called thin film encapsulation, or TFE. It's basically a microscopic, multi-layer shield that they build right on top of the pixels. It alternates between flexible organic layers and super dense inorganic layers. This creates a kind of labyrinth that's almost impossible for water or oxygen molecules to get through. And this breakthrough isn't just about protecting the pixels. Because it's so thin and flexible, it's the key technology that actually makes things like foldable phones possible. Okay, so we've been deep in the weeds on the microscopic stuff, but let's zoom all the way out. Where does all of this happen? Because the environment needed to do this kind of manufacturing is honestly just as incredible as the technology itself. Welcome to the display fab, which is short for fabrication plant. These places are some of the most advanced and controlled environments on the entire planet. They're defined by three main things: a level of cleanliness that is hard to even comprehend, almost total automation, and, well, they're incredibly thirsty and hungry. They use insane amounts of ultra-pure water and electricity. So how clean are we talking? Well, many of the key areas are rated as Class 10. That means in a cubic foot of air, think about a box about this big, there are fewer than 10 particles that are half a micron in size. Your hair is about 70 microns thick. In this world, a single speck of dust isn't just a speck of dust. It's a giant boulder that can wipe out an entire neighborhood of transistors. And because we humans are basically just big, clumsy bags of dust and particles, we aren't allowed anywhere near the action. The whole process is automated. Those giant sheets of glass float through the factory, moved around by this incredible ballet of robotic hoists in the ceiling and automated vehicles on the floor. From the second that raw glass enters the clean room to the moment a finished display leaves, it is never, ever touched by a human hand. All right, we are almost at the finish line. The screen is nearly complete, but there's one final, massive challenge to overcome. In a process with billions of parts and hundreds of complicated steps, how do you make sure every single one is perfect? Well, the answer's pretty simple. You get a defect, a dead pixel or a bright pixel or a thin line that just won't go away. When you have billions of chances for something to go wrong on every single sheet of glass, getting a high yield of perfect screens is the ultimate battle. It's where companies make or lose all their money. And the way they deal with this is just breathtaking. First, they use something called automated optical inspection. These are systems with super fast cameras and AI that scan every square micron of the panel, creating a complete map of every single potential flaw. But here is the part that just blows my mind. They can actually repair some of these defects. They use incredibly precise lasers to perform microscopic surgery. They can literally zap away a tiny short circuit. Or, and this is incredible, if there's a break in a wire, they can use a special gas and a laser to essentially 3D print a microscopic metal patch to fix it. They are literally repairing wiring that is too small for us to see. So when you really think about it, the journey is just immense. It starts with a sheet of glass larger than a person, goes through hundreds of steps to build a perfect city of billions of electronic parts, and ends with lasers performing microscopic surgery, all so that the image you're looking at is flawless. It's really no exaggeration to say it's one of the greatest manufacturing achievements in human history. It's this beautiful combination of physics, chemistry, and engineering that's been refined for decades. And as the technology keeps getting better, giving us screens that are transparent, flexible, even stretchable, it just leaves you with this really exciting question: what are we going to build with it next?